Good morning, everyone. Welcome to the first press briefing of the day for January 7th. My name is Tarini Konchady. I'm the AAS Media Fellow. AAS Press Officer Rick Feinberg is at the back of the room. He'll be monitoring the chat for the live stream. I'm going to ask you to silence any devices that may make noise. There will be 3 press releases associated with this briefing going out. They should be in your inboxes by the end of the hour. Before we get into the thick of things, there are some announcements. This afternoon's briefing with representatives from the Mauna Kea observatories and the 30-meter telescope will be an off-the-record backgrounder, restricted to press registrants only, and will not be live-streamed. You can see the online press kit for more information. So if this is your first time at a press briefing, the way this works is I'm going to introduce the speakers and their topics. They're going to give their presentations in succession. We're going to open up the room to questions, and we'll also be taking questions from the chat. So the subject of today's briefing is the Milky Way inside and out. We're going to be hearing about new events and features that have been found in our home galaxy. In order, the presentations are a new feature of the galaxy revealed by 3D dust mapping, which will be given by Alyssa Goodman of the Center for Astrophysics at Harvard and Smithsonian. The next presentation is Eagle-Eyed View from Flying Telescope reveals how the Swan Nebula hatched. The speaker will be James de Buizer, and his co-author, Wanggi will be available to answer questions during the question and answer session. They are from the Sophia Observatory and the University Space Research Association. The next presentation is discovery and characterization of a recent star formation event far into the Milky Way's halo. That will be given by Adrian Price-Whelan of the Flatiron Institute. And the last presentation is titled Follow-up and Implications of a Recent Star Formation Event Far into the Milky Way's Halo. That will be given by David Nidever of Montana State University. So without further ado, I will turn it over to the speakers.
Good morning, everybody. I'm really pleased to be here. We've known about the result I'm going to tell you about for quite some time, and we've been having a hard time keeping it quiet. A lot of people here actually already know, but don't tell anybody. Anyway, what I would like to do is first explain, is first explain that I'm here representing actually a really significant collaboration. And you see the names on the screen, and you can find that all in your press materials. And the 2 people who are absolutely most key to the Nature paper that I'm going to be talking about are João Alves, who's the first author, who's in China giving a class right now, and Catherine Zucker, who's in Florida on vacation. But I brought the key developer of the 3D dust mapping technique that I will talk about, Professor Finkbeiner, over here in the first row. So you can also ask him questions later. So what is the Radcliffe wave, and what is 3D dust mapping? So I thought I would start by just showing you what we think the Milky Way looks like. And so what you see here in the background is a cartoon model of the Milky Way. A lot of people think this is an image of the Milky Way, probably not a lot of people in this room. But it's our cartoon model based on data. And then only the red dots that I'll show you in this movie in just a minute are the actual measurements that I'm talking about today. Okay? So this is, roughly we think that the Milky Way is a spiral galaxy. We really don't even know how many arms it has or how well defined they are. But those red dots there mark the positions, the very accurately measured 3-dimensional positions of clouds of gas, dense gas, that form stars in the Milky Way. So these are famous clouds like Orion and Perseus and things that you know the names of. And I'll show you some interactive figures later where you can actually see which cloud is which. But you notice that from the top, looking above the galaxy, it's a very straight feature, much straighter than a curved spiral arm should be. And then from the side, it has this weird damped sine wave-like structure. And perhaps the oddest feature is how close it is to the sun and that we didn't know about it before. Okay. So it is 9,000 light years long, 400 light years wide, look at end on, it goes 500 light years in and out of the plane of the Milky Way. So much farther out of the plane of the Milky Way than we would have thought. So this is a very odd and unexpected feature. And what it's based on is a whole set of new distance measurements using a technique that, again, Doug and his group have pioneered for the last decade or so. And it now has been enhanced with data from Gaia, which I'll show you in just a minute. So really what we can do now is measure distances to about 5%, where it used to be several tens of percent uncertainty to measure the distances to these gas clouds. And that's what lets you find features like the Radcliffe wave, which is probably just one of many strange structural features we'll use using this technique. So the skeptics in the audience might say, oh yeah, but are these distances any good? And the experts here will know that the gold standard for measuring distances to star-forming regions in the Milky Way is proper motion observations of masers. And I'll just tell you that what's on the y-axis of this plot is those gold standard observations, and on what's on the x-axis of this clearly one-to-one line is these dust distances. The reason there are so few points is because masers can only be seen in very special locations where this mazing phenomenon happens, whereas dust associated with these gaseous clouds is everywhere. So it's much more useful, the 3D dust measurements, for mapping out structures throughout the galaxy rather than in just special regions. So this is just a little cartoon that gives you the idea of why we were able to do what we did. So if you just wrote down, without the uncertainties, the positions of a whole bunch of nearby star-forming regions, you'd get, there's the sun, the yellow dot, and the regions are these red dots, and they're kind of scattered around, and maybe they're associated with some arm, or people thought that there was this thing called Gould's belt, which was an expanding ring of gas around the sun. But the reason that there was such uncertainty is because the distances were very highly uncertain, and in fact, those dots could have been anywhere along those lines. The reason the lines point in that odd direction is because the distance uncertainty is radially from our location, essentially at the position of the sun. So then what happened? So these 3D dust mapping techniques got better and better on their own. I'll show you how they work in just a minute. And then Gaia was added as a constraint on the distances to stars, which really helps those techniques. And so what happened was you went from that kind of uncertainty to that kind of uncertainty. And so now you can clearly see, so this would be what the Radcliffe wave looks at sort of from the side, what feature I'm talking about. Okay. And so how did we do this? I mentioned several times 3D dust mapping, Gaia, and then GLUE and Worldwide Telescope. What are those? Those are software packages that were really important to actually see what was going on. And at the bottom there, and I should mention these slides are all available on a website that I'll put the URL up for at the end. You can see the acknowledgments to all of our funders and software providers. And I don't have time to tell you about that, but I'll be happy to talk about it afterwards. Anyway, how does 3D dust mapping work? Let's say you have a telescope, hopefully a little bit bigger than that one, and you're making an image, and you pretend, the image is the parallelogram, you pretend that a star has some color. And by the way, as a helpful visual aid, I have worn this shirt for you to explain this. So anyway, so you pretend that, say you have a star that's green out there, and then there's this cloud of dust out, which is mixed with gas. So dust and gas in the interstellar medium are typically mixed together. So I might say dust, I might say gas, but it's the dust that's causing what I'm going to show you. So you have this dust out there, and when the light from the star gets to your imaging plane, its color changes just a little bit. So it starts out green, and it winds up a little bit reddish or more brown by the time it gets to you. And so that phenomenon is called reddening, and that reddening is similar to what you see in a sunset when you just look at the sun through our atmosphere with its particulate matter. And so what you can do is you can say, well, let's imagine, which they're not, okay, but that all the stars were the same color and that there's this distribution of dust and that by the time the light from those stars gets to you, they've been changed by different color amounts. So you can have extremely brilliant graduate students in algorithms and lots of computing and Doug Finkbeiner, and you can figure out a self-consistent answer to what the colors of those stars really should be and how their colors are changed by dust at various distances along the line of sight. And then you can actually do a much better job if you cheat and you actually know the distances, okay? And so Gaia has provided three-dimensional positions and velocities in many cases of stars throughout the Milky Way and many that are in the region that we're looking at when we look at the Radcliffe wave. And so that is what allows these distances to be so super accurate. And if you try to just take all of the data at once and make a view of what the Milky Way looks like from above and below near the sun, you get what is shown in this video that was created by Greg Green and is in that paper that's referenced there, Green et al., 2019. So that video is actually using a slightly lower resolution approach than what we use to get the super high distance resolution that we use to find the Radcliffe wave. But just to give you some idea of how the software works, this is just a screenshot of Worldwide Telescope, which has a display downstairs at the AAS booth if you want to know more about that, inside of this program called GLUE, which is funded by NASA and was developed originally for the James Webb Space Telescope. And what that lets you do, you see a big long list of data sets on the side, is combine the features of many different data sets and visualize them in many different ways, and then share what you find with others. And so our big aha moment for this was when we first put the three-dimensional distribution of these clouds into the context of the galaxy using Worldwide Telescope in GLUE, as I showed you in the movie in the beginning. That was actually made using Worldwide Telescope. So here's Worldwide Telescope again in GLUE, and you ask this question, which I'm sure you're wondering, why, if this thing is right up in our face, did we not see the Radcliffe wave sooner? And really, it's not apparent in 2D. So we've been talking to a couple of reporters the last few days, and they're asking, well, how can we look up and see this on the sky? And it's like, well, first of all, you can't because it's dust clouds, okay? But also, it's all over the sky. Like, you can't just look in one position, and it doesn't make sense unless you can see it in 3D. Okay? So the other answer to why we couldn't find this sooner is these maser VLBI techniques I told you have been around for 20 years or more, but they only apply to very special regions. So you couldn't have enough sampling on the sky to do this. The Worldwide Telescope software that I showed you was developed in about 2008. The 3D dust mapping technique started about 10 years ago, and the publications from it started about 5 years ago. And GLUE's 3D capabilities were also starting to be useful about 5 years ago. And then the second data release from Gaia was just a couple of years ago. And I'm sorry, but it took us a little while to do the work. You know, it's not instant. Okay. So anyway, what you can find in the paper that was just released on Nature 20 minutes ago or so is interactive figures, which I can show you, I think, there's a problem here where I can't, I got it, okay. The cursor has to, I can't, great. I see it on my screen, but I wonder, wait, I can be really clever, I think. Hang on, I can do this. Look at that, I'm gonna defeat the AAS's system. If only I put my glasses on. All right. Sorry, Rick. Okay, so here you go. So you can actually interact with all of the data if you want, and you can, do you have any idea how hard it is to see this from where I'm standing? Okay, so you can turn off the clouds that are not part of the wave, and you can ask me later how we know that those aren't part of the wave, and you can even turn on a fit of an actual damped sine wave to the Radcliffe wave. So that's pretty great. And I have kind of no idea how to get back now to my slides. So I'm just going to do this, and hopefully that'll work. That's okay. I have this whole, I got this worked out. Okay, I only have like 2 slides left, and then I'll move on to, we will move on rather to these other fascinating presentations. So let me just show you here at the end. Great. Okay, so you want to know what this means, right? So I didn't want to just stop. Okay, so the so what of all of this for astronomers is, first of all, the demise of this thing called Gould's belt, which was this idea that there was kind of a ring of gas around the sun. It turns out that was really a projection effect, and it's just kind of the sloped part of the Radcliffe wave viewed from the side. The local arm is not what we thought it was. It turns out it's this gigantically straight feature. For astronomers, I'll say it's 2.7 kiloparsecs long, goes 160 parsecs out of the plane. So that's very, very strange. It agrees again with the maser distances, so this is not actually controversial, okay? And this wave in the arm was basically not predicted except by models like, where's Gus? Gus Bean, who's a graduate student at Harvard right here, and other people here have actually worked on collisions of massive things with the Milky Way. And you can actually get things vaguely like this, not exactly like this, from those kind of collisions. And so that actually brings me to the last set of questions, which is what is the origin, what are the open questions? So what's the origin of this thing? I just mentioned that it could be a collision, something falling down onto the Milky Way. We have some constraints on what that could be that would cause that kind of oscillation, but not a lot. So basically it's an open question what the origin of this is. Whether other parts of the Milky Way show this, you notice how close this is to the sun, so this was the easiest place that we would be able to see something like this, right in our local arm. We might be able to see this in edge-on galaxies if we had a very clever way to resolve distances. We don't know, But we can think about how to search for that. And we also don't know what this means for star formation in galaxies, because this is a relatively young feature, and all of the regions that are in it are associated with regions that are forming young stars. So there's much more to know, and we have this website that's called Surf the Radcliffe Wave. We were in Hawaii. We thought we should let you surf. But in fact, it turns out that if you actually calculate the orbit of the sun and the orbit of the Radcliffe Wave, they cross each other, if you trust the calculations, about 13 million years ago, and might even cross again in the future. So we kind of almost are surfing the Radcliffe Wave. And I will say more about this apparently at 6:10 tonight, when there's this iPoster Plus presentation in the iPoster Theater. And again, I refer you to my colleague Doug Finkbeiner here for questions about 3D dust mapping, to Gus for questions about collisions. And these are the two people who really wish that they could have been here with me today. So I'll just say thank you very much. Bye.
All right, so hello, I'm James Buizer, and I'm the lead investigator of a project where we're observing the largest, most massive star-forming regions in our galaxy, the Milky Way. And one of these regions that we were looking at is the Swan Nebula, and it's the subject of this presentation and of a paper that is about to come out that was led by my postdoc, Dr. Wanggi Lim, who's here today as well. The new infrared data that we collected for this study is the highest resolution or highest magnification observations yet achieved at these wavelengths. And so I'm starting here by showing the beautiful composite image that we were able to create of the Swan Nebula from our new data and from some ancillary data. Of course, the main objective here was to catalog and analyze the nature of massive and young stellar objects. And thanks to the exquisite detail that we had in this data, we were able to uncover several regions that have never been several stars that had never been before seen. At the same time, we were, even though this nebula looks like it's all one contiguous object, it actually is not. It is made up of several star-forming subregions or star clusters that formed at different times. And it's the confluence of these multiple events that led to the present appearance of the Swan Nebula. Well, now that you have the punchline, let me go to some background for some perspective. Again, these images were motivated by wanting to look at the most massive star-forming regions in our galaxy. So what is a massive star and why do we care? A massive star is any star that's 8 times the mass of our sun or larger. The largest star that we know of is about a 300 solar mass star. And stars that are in this 8 to 300 solar mass range only constitute about 1% of all known stars. And so you might ask, well, if there's so few of those stars, why do we even care about them? And the answer is that while these stars are rare, they are extremely energetic throughout their lifetimes, and they have a huge influence on their environments. And in fact, these are the same stars that end their lives as supernovae. So from cradle to grave, they have a huge amount of energy that they release, and that can change the entire chemistry or the evolution of entire galaxies. However, their rarity means that we only have a small sample for study, and so we know relatively little about them. And in fact, the part that we know least about is their formation, because in addition to them being rare, they form in the densest and darkest parts of our galactic neighborhood. And so these stars form in obscurity, and their light has a hard time getting out of this dense gas and dust to be seen at most wavelengths. However, the infrared can pierce through this veil of gas and dust, and that light can get out for us to see the stars and see their environments. And so we need an infrared facility to get these observations, and we use the SOFIA Observatory for these observations. SOFIA is unique. It is a flying telescope. It's a 2.5 meter infrared optimized telescope that flies inside a Boeing 747 aircraft. And as I said, this was one of several sources that we looked at. The Swan Nebula is also known as M17. It's located in the constellation of Sagittarius. It's a little bit more than 5,000 light years away. And I'm showing here you a backyard telescope image of the Swan Nebula. It's very, very bright. You could see it with binoculars. And maybe you can see why it's called the Swan Nebula. And if you can't, I'll visually cue you here. Now, this is a nice way for you to see the swan. However, professional astronomers like to look at things north up. And so I will rotate things to how the nebula looks like in the image that I showed you and for the rest of this talk. But what we're seeing in the optical light image here is actually light from an older generation of stars at the edge of a very dense cloud of gas and dust. And that's the area that's in the green contours that you're seeing here. And you can see it's very dark in the optical image, but this is where the newest generation of massive stars are forming. And so this is where we wanted to look with SOFIA, and this box is about the size of the sky that we looked at with SOFIA. And we looked at it in the infrared, and in the infrared, this dark area in the optical light actually lights up from the heat of the stars inside it to give you the view that looks like this. And so this is the highest resolution infrared image ever obtained of this nebula, the entire nebula at 20 microns. This is not the first time it's been observed at 20 microns. I can show you what it looked like with previous observations. This is a Spitzer Space Telescope observation. And while it looked at a comparable wavelength and has a comparable resolution or magnification, the nebula was so bright that it saturated or overexposed the images. And so all where you see this black is there's no information, and it's basically the entire nebula. The best image that we have of the entire nebula at this wavelength comes from the Mid-Course SpaceX Satellite Experiment, or MSX. This was a small space telescope, and so it doesn't have the resolution or magnification that SOFIA has. In fact, when I go between this best image prior to SOFIA to the SOFIA image, you can see the tremendous amount of new detail that we are seeing in the nebula at these wavelengths. Now, we also took data with SOFIA at 37 microns, and this is what it looks like there. And here you see a unique image of the Swan Nebula never before seen. There's no comparable image that has ever existed of the Swan Nebula at this wavelength. And thanks to the high resolution of these studies, we were able to identify and study the characteristics of the massive stars that are forming here. In fact, some of the bright peaks of light that you see here are the brightest of the massive stars, or the more obvious ones that we're talking about. Now, the beautiful composite image that I started off in this talk showing you is made up of taking this 20 micron image and color coding it blue, taking the 37 micron image from SOFIA and color coding it green, adding in a Herschel 70 micron image in red to give you this beautiful image that you see here. And we also threw a star field over the top of it, which is a near optical image from Spitzer that is not saturated. Now, I also said we learned something about how this nebula evolved. And so we discovered that this nebula is not actually one nebula. It actually is a bunch of subcomponents that are in different evolutionary stages. The central region that's encircled in green is the oldest area, and there's very little gas and dust there. That's why it's faint, because a population of stars has already formed there and depleted most of the gas and dust. And it's actually those stars that are responsible for heating the nebula, and that's why it's brighter on the inside than on the outside of the nebula. The next youngest area is this clump of material way up to the top, and that's surrounded in a pink circle. The next youngest area is the northern bar, which we encircled in blue. And then the youngest area is the yellow encircled area, and this is known as the southern bar. And this is actually where we found the vast majority of our new massive stars that had never been seen before. So to summarize, we have taken beautifully detailed images of the Swan Nebula that allow us to uncover for the first time a previously hidden population of some of the most massive and youngest stars in the Swan Nebula. And we have characterized them, and that was the subject of our paper. But also along the way, we found out that this is not one monolithic structure, and that there's a confluence of multiple stages of cloud and star formation that came together all at once to create what we see today as the Swan Nebula. Thank you.
Hi, so I'm Adrian Price-Whelan. I'm a postdoc at the Flatiron Institute in New York. You can see I'm still in my New York attire. I haven't made it to Hawaii. And you'll also see in a minute why I wish I was wearing Alyssa's shirt, actually. So I'm going to be telling you the first half of a story about the discovery and characterization of an interesting star cluster that David and I found and worked on. He's going to tell you the second half, and together we're also going to tell you a bit about why this is important for understanding the future fate of our galaxy, the Milky Way, and for the demise of our largest satellite galaxies, the Magellanic Clouds. So when you think of the Milky Way, and we've had a great introduction from Alyssa as well, you probably think of an image like this. So this beautiful long exposure image of the Milky Way over Oahu. That is an image that probably comes to mind is our perspective of the Milky Way from within the disk of the Milky Way itself. But if you could travel very, very fast and go out of the Milky Way and look at it from beyond, it would probably look something like this galaxy. So I didn't use the same cartoon that Alyssa used. I used another galaxy as a reference. This is NGC 3953. So we have a disk, we have a barred distribution of stars in the center of our galaxy, we have spiral arms, and to scale within this galaxy, the sun would sit about here. So up until very recently, the total volume within which we, as astronomers and you, had access to very precisely measured stellar motions on the plane of the sky, or proper motions, was a very small region, just very locally around the sun, and that was from the Hipparchus mission, which operated in the late 80s and early 90s. All of that changed very recently, as was mentioned already, thanks to the European Space Agency Gaia mission, which was launched in 2013, and it's still operating now. The equivalent volume within which Gaia can measure the same kind of precise on-sky motions, or proper motions, is about 1,000 times larger. So it's closer to a few 100,000 light years in size around the Milky Way. And that means Gaia can measure these properties throughout essentially the entire galaxy, the entire Milky Way, and even beyond. So the main data release that we have for Gaia is data release 2, which was released in April of 2019. That data release contained about 2 billion parallax measurements, or distance measurements, these proper motions that I mentioned before, and stellar colors, along with a bunch of other information for a subset of the stars. So I've spent the majority of the last year and a half or two working with data from this data release 2. I think there's still a ton more to do. But when new data sets come out that are this transformational, it's useful to stop and think about what the low-hanging fruit are before you start thinking about the very hard problems. And so I had an idea, which is not a new idea by any means, but now that we have all of this great data, I thought it would be fun and easy to look for new star clusters around the Milky Way. So how do we do that? So we know how stars and star clusters line up in the space of their colors and their brightnesses, or their temperatures and their luminosities. So here's some examples. The points here show individual stars, and the different colors are different known star clusters around the Milky Way. These are young star clusters. So that with your eye here. But they also importantly contain these relatively rare blue or very hot stars that we just heard about, which is unlike the typical old stellar populations that you see throughout the Milky Way. So if you want to search for a star cluster, it's useful to search in rare types of stars because that removes a lot of the contamination that you have to contend with. So if you look for blue hot stars, you'll probably be able to find the star cluster with less confusion from the background. So this is why I was thinking it would be nice to have Alyssa's shirt here. To illustrate this, I made a fake image of the sky in a small region. So in a typical field, you typically have a superposition of many different types of stars at many different distances. So even if there were a star cluster in this image, it would be hard to see because of all the other intervening stars. If you select only blue stars, right away that removes most of the things that are in your image. It removes quite a bit of the contamination, and you already might be able to notice that there's a slight overdensity of stuff in the center of my fake image here. But the real power of Gaia is that you can go beyond colors, which is what you're limited to from large imaging surveys. We can use the motions of stars directly to start correlating them to look for little collections of stars that are actually moving together, as they would be if they were in a bound stellar cluster. So you might notice also that the central stars that you saw before all share the same velocity in my cartoon. So we found a new cluster. So that was obviously a cartoon, but that was essentially the procedure that I used to discover a new star cluster that I'm going to be talking about here. So this is the stars in the cluster here. This is showing, again, the color brightness diagram on the left and sky positions on the right. The stars in the cluster are shown as blue points over all the background stars shown in gray. So you can see that the cluster has a sort of well-defined sequence in this color brightness diagram, and all of the stars seem to be moving in the same direction, as you can see from the arrows that suggest in the right-hand panel. Notice also that this looks like sort of the tip of the bluest stars in the main sequences of the star clusters that we saw before. So this kind of gave us confidence that this is actually a real object. So from doing some detailed modeling of the population of stars that are in this cluster and using their brightnesses, we were able to determine its characteristics. So I'm going to summarize the sort of key parameters for this cluster. So its age is about 120 million years. So that's actually very, very young in astronomical terms. And it's fairly small, a little over 1,000 solar masses, so 1,000 times the mass of our own sun. These are actually fairly typical parameters for an open or a young star cluster in the Milky Way disk. So for example, these are comparable to the properties of the Pleiades, which is a star cluster you might be familiar with. It's fairly near to the sun. Very much unlike the Pleiades, though, this thing that we found is extremely far away. So the Pleiades is about 400 and or so light years away. This object is 94,000 light years away. So this is about 200 times farther away than the Pleiades, which is sort of the typical distance to these young clusters that we see in the disk. Other unusual things relative to the Pleiades or relative to the sun is that it has a very low metal content and it's very large. So it's 1.5 degrees on the sky, but it's much, much farther away than the Pleiades. So it's in a physical sense, it's about 1,600 light years across, which is about 100 times larger than the Pleiades. So where is this thing? So another big surprise is that, again, unlike the Pleiades and all other known young stellar clusters in the Milky Way, this object is very, very far away from the galactic disk. So it's very far from the midplane of the galactic disk. But it's also young, so it didn't have time to form somewhere else and then end up where it is today because it was born recently. So it probably was born somewhere near where we see it now. So the question is, how did it form there where there's very little cold gas that you need in order to form a new generation of stars? And the clue, so I should say that here in this visualization, the cluster that we found is the blue points, which are sort of connected by a line to that circle. And this is a simulation of the Milky Way shown with stars shown as white points. The clue to what we think the answer is lies in the purple points, which are below the Milky Way disk. Those are meant to represent stars in our two largest satellite galaxies, the Large and Small Magellanic Clouds. So the Magellanic Clouds are dwarf galaxies that are thought to be orbiting the Milky Way, but on their first approach. So they're coming in for the first time into the Milky Way. So these are the two clouds right here, the large on the left and the small on the right, circled in red. And over the next few 100 million years, the gravitational influence of the clouds as they orbit around the Milky Way will significantly alter the structure and the future history or future evolution of the Milky Way. So it's therefore critical to understand these satellite galaxies and their infall in order to sort of place the Milky Way in context and understand the future of where we're going. So the last image showed stars in the Magellanic Clouds, but if you could instead see gas, neutral hydrogen gas, instead of the radiating stars that we saw before, the clouds look actually a lot more interesting. So the two clouds are pointed out in the bottom right of this image. But if you could see all the neutral hydrogen gas, you'd see that they're surrounded by and connected to this huge stream of gas that extends behind it and in front of the clouds. This is an image from David Nidever from a few years ago. Importantly, though, this gas that's being stripped and is emanating from the Magellanic Clouds is ending up in the halo, or the outskirts of our Milky Way, which is where we found this cluster. So to return to the puzzle of how could a young cluster of stars have formed so far out away from where most of the gas and young stars are in the Milky Way, this is one possible answer. It also turns out that the location of the cluster is just beyond the tip of what we call the leading arm portion of the Magellanic gas stream. So it's also very suggestive of being associated with this gas. So this would be very exciting because it's very far away from the clouds themselves, and it therefore allows us to constrain the distance to the Magellanic Stream, which is an otherwise elusive property. It's not something you can measure for gas directly. You have to use techniques like the things Alyssa showed. So there's simulations, though, that try to reproduce the sort of on-sky distribution of gas. Those make predictions for how far away the stream is. And now, so I'm showing you that from one particular simulation, the predicted distance for, along the Magellanic Stream. Now we can place a data point on here because we have a distance to this star cluster if it is associated with the gas. And interestingly and excitingly, we find that it's actually much closer to the sun than would be predicted from these simulations. So this will lead to improved models for the infall of these two galaxies. So the one caveat, which David will talk about, is that we don't actually know for sure if it's truly associated with the gas. because we only have the on-sky motions measured for the stars, whereas for the gas, we only have the line of sight motion measured. So we don't actually have all components of the velocity in order to say that these things are actually moving together and therefore associated. So to summarize the first part here, so we found a young star cluster far away from the Milky Way disk, where all the other young star clusters we know of are found. We think this thing was formed in the gas stream originating in the Magellanic Clouds, but we still need line-of-sight velocities in order to confirm that the stars are actually moving with and therefore associated with the gaseous Magellanic Stream. But excitingly, these would be the only stars that have been found in the stream and therefore give us a key and critical distance measurement to the gas in order to improve updated models of the system. So that's it.
Hi, my name is David Nidever. I'm an assistant professor at Montana State University, and I'll be discussing the follow-up and implications of the cluster that Adrian just found. As Adrian just mentioned, with the Gaia data and photometry alone, it was still a bit unclear what the origin of the cluster was, and to fully answer that question, we needed extra piece of information, and that was spectroscopy. So just as a quick reminder, we perform spectroscopy with a spectrograph. And the telescope collects the light from a star and then sends it through the spectrograph, which is basically just a fancy prism. So this spreads out the light into its constituent colors and creates a spectrum like you see on the bottom here. And this is what the solar spectrum looks like. A stellar spectrum has a lot of these dark lines in them, as you can see here in the vertical lines. And Fraunhofer first noticed this in 1814. And these are produced by atoms in the outer atmosphere of a star, absorbing light at very specific wavelengths. Now we can use these absorption lines to actually measure the abundance of heavy elements in a star. So this figure here shows two different stars, two different spectra of stars with the overall shape removed, and they've been vertically offset to be able to easily intercompare them. And as you can see, the black spectrum has many more dips or absorption lines than the red spectrum, and that's because it has a much larger number of heavy elements. So that's one thing we can do with the spectra. The second thing we can do is we can measure the line of sight or radial velocity of a star using the Doppler shift. So with these two pieces of information, we'll be able to better understand the motion of the cluster stars and their origin. So we used one of the 6.5 meter diameter Magellan telescopes in Chile to obtain spectra of 28 of the brightest stars in the cluster. And here are two examples of spectra that we obtained in the black and the best fitting models in red. And using these spectra, we were able to derive the properties of the 28 brightest stars. So what did we find? We found that the properties were consistent with the 116 million-year-old ages that Adrian found from the photometry. And again, this is consistent with the Pleiades, the age of the Pleiades cluster that you see here. So this is quite young. And so it's quite unusual to find out in the halo of the Milky Way. We also were able to determine the content of heavy elements in the cluster and found that it was 6% of the suns. And now this is quite low, and as you can see in this diagram here, the heavy element content of stars, of cluster stars in the Milky Way has been continuously increasing with time, but the cluster stars fall away below that. So that's a bit unusual. However, it really nicely matches the known heavy metal content found in the leading arm and the Magellanic Stream. So that fits together quite nicely. Finally, we measured the rate of velocity of the stars, and it was quite high at 277 kilometers per second. And this is also consistent with the known velocity of the leading arm, which you can see in this diagram here. So this is showing the rate of velocity of the gas in stars versus angular distance along the Magellanic Stream, with the stars in red and the gas in blue. And you can see that they quite nicely match up. So all this evidence taken together indicates that the cluster stars, the Price-Whelan 1 cluster stars, were born in the leading arm gas, and this is the first time anyone has ever found stars associated with the Magellanic Stream or leading arm after over 3 decades of searching for it. So this is really an exciting result. But if you look at this plot a little bit more closely, you can see something a little bit peculiar. You can see that the stars are spatially offset from the gas and a little bit in velocity as well. So what's that from? Well, it's actually quite expected because the Milky Way is surrounded by a hot corona of gas at about 1 million degrees. And as the leading arm gas moves through it, it experiences drag, but the stars do not. So over time, the gas slows down and falls behind the stars, and we should see this separation both happening spatially and in velocity. And this will be, the separation will be increasing over time. So if we look at the spatial distribution of the stars and the gas on the sky, we can see that they are separated. But what is the exact spatial offset, and where were the stars actually born? Well, it turns out that if you shift the stars relative to gas by the right amount, the spatial structures actually line up like this. So with an offset of about 10 degrees, or 17,000 light years, the clumpy and elongated structures of both the stars and the gas line up quite nicely. And we can see that the densest stellar clump aligns with the highest density knot of gas. Now we have the full velocity information of the cluster, both the proper motions and the rate of velocity, and we can use the offset between the gas and the stars to actually determine the density of the Milky Way's hot halo quite precisely. And what we found is that it's actually 10 times more dense and more massive than previously thought. Finally, as Adrian mentioned, the Magellanic Clouds are falling into the Milky Way and will soon merge with it. And this is beautifully illustrated in this computer simulation by Christina Besla that shows the formation of the Magellanic Stream and leading arm from the interaction of the Magellanic Clouds with each other, and they're falling into the Milky Way, which is seen at the center here, edge on. But with the cluster, we now know the distance of the leading arm very accurately, and it's significantly closer than previously thought. And this indicates that the merging, especially of the gas, will happen sooner than predicted, and will soon replenish the Milky Way's gas reservoir, which will allow it to continue to form stars over a longer time. So in summary, we made the first detection of stars born in the leading arm of the Magellanic Stream after more than 30 years of searching for it. We were able to use the offsets between the gas and stars to measure the density of the Milky Way's hot gaseous corona and found that it's 10 times more massive than previously thought. We also accurately determined the distance of the leading arm and found that it's significantly closer than expected. And that closer distance implies that the Magellanic Clouds and stream will merge with the Milky Way sooner than expected and replenish the Milky Way's gas reservoir. And I'll just end with a note that both of our papers have been published in the Astrophysical Journal recently. Thank you.
Okay, thank you to all the speakers. We'll now open the floor to questions. Before you ask your question, please state your name and affiliation, and wait for the mic for the benefit of those on the live stream.
Good morning. It's Camille Carlisle from Sky and Telescope. Okay, several questions. First, for Alyssa, could you compare this structure to other wave structures we've seen that we think may be from merger or interaction activity? And you mentioned something about the local arm not being what we thought it was. Could you clarify that?
Absolutely, sure. So what I can say is that in terms of coherent gas structures, this is the largest thing we know about in the Milky Way. And so it was a sample of one at the moment, okay? But we sat down at one point with Mark Reed, who you may know is like the world's expert on measuring the structure of the galaxy, and Tom Dame also together. And we looked at where the Radcliffe wave was relative to the local arm as defined by masers. And on a very large scale, the masers show a fit, a log normal spiral fit to the arm going kind of all the way, not all the way around, but a significant number of degrees around the galaxy. And the Radcliffe wave, that arm like this kind of crosses it like this. You can see it, you can turn it on, an interactive figure. And so first, we're like, oh, maybe this is some sort of spur off the local arm. But then when we made that plot comparing the actual distances of the masers and the clouds, where you can compare them, it's a total one-to-one correlation. So the arm that was defined by masers defined very low resolution, sparse data around the whole galaxy. And this is a very high resolution view, very locally. And so it has this very long straight feature. And in some other talks I've given, I actually compare it to a galaxy that is one of Mark's favorites. And you can find that online too on the website, which I should have said is tinyurl.com/radwave. But anyway, you can see pictures of other galaxies that have these long straight features in the spiral arm. So what we think is that the local arm locally, that the Radcliffe wave is not some spur off the local arm, but Mark and Tom and everybody in the room agrees is the local arm. The Radcliffe wave is the local arm locally, and it is this very long, straight feature. And if we could see the galaxy from the outside, it would look like one of these external galaxies that has a straight piece. So. The other thing I forgot to say, it's very important, so I'll just say it. Somebody's going to ask me why this is called the Radcliffe wave, right? And the answer is because the work was done largely at the Radcliffe Institute when João Alves was a fellow visiting Radcliffe. And he wanted also to pay tribute, which is wonderful, to the early women astronomers at the Harvard College Observatory, whose work really, one of them, Henrietta Leavitt, for example, allowed the measurement of distances and who were affiliated with Radcliffe, almost 100 years ago. So anyway, thank you, Radcliffe.
Leslie Sage from Nature for James. I just wanted a quick clarification. You said the most massive star known was 300 solar masses. Don Feiger did a quite careful study 10, 12 years ago when the most massive he found was 120 solar masses. So where is this 300 solar mass star?
Yeah, I gave the name of it in my slide. I don't recall it off the top of my head. But that is the largest one that we know of. Yeah, 300 solar masses.
Hi, this is Ethan Siegel, starts with a bang in Forbes. This question is either for Adrian or David. I don't care which of you take it. How and why are you so confident that these stars that you've just discovered are from the Magellanic Stream and not from the gas in the halo of the Milky Way?
So most of the gas that's in the halo of the Milky Way is very hot, as David mentioned. It's heated to over 1 million degrees or so, and so you just can't collapse and form stars out of that gas. You need colder or molecular gas even. If you look at where all the cold gas in the Milky Way halo is, it's 95% or so in the Magellanic Stream. So it's just if you think of it in that terms, it's kind of the most likely place that you would form new stars if you were going to in the halo. So there's not a lot of other cold gas out there, I think is the short answer.
And as you saw in the rate of velocity plot, there is some gas at lower velocities, but that's much closer to us and in the Milky Way disk. So yeah, the Magellanic Stream and leading are the only thing out there for where you can form this. And all the evidence we found from the velocities, from the heavy metal content, and also the offset all makes sense with it forming in the leading arm.
I actually want to add some words on Leslie's question. So in 2000, I think it's 2012 or 11, Zhang et al. Actually found a 300 solar mass star from the other Magellanic Cloud. And then we still are quite doped because we basically do not really know that if it is really single or binary. So I think you basically raised a really important question.
I think we had a question there.
Thank you. Hi, I'm Jacob Bueller, recent student at the Phillips Academy. This question is for Dr. Buizer. Is that how you pronounce it?
Buizer.
Buizer. I'm sorry. But I was
Happens
just
all the time. Don't worry about it.
I guess this is kind of a comprehension thing, I guess. But when you're talking about the Swan Nebula you had a big diagram of which sections of it were like youngest, oldest, et cetera. Like how do you know how do you know the ages of each section?
I'll let Wanggi talk about that. He did the analysis.
Yeah, okay, excellent question. So we basically compared two independent evolutionary tracers for the protoclusters. So one called as the Buizer analysis. So we just compared the kinematic energy to the gravitational potential energy. So if you see the more kinematic energy, we basically see that, okay, so there are more stars, so they are actually generating more feedbacks. So like the kinetic energy will be just like going up. So then like if you see higher the Buizer parameter alpha, then you will actually think, okay, so like this is the kind of older population. And also we also compared to the other L over M, volumetric luminosity over the other mass of the dust. So this also says that like if you have like a more stars inside the protocluster, then like you will have like a brighter protocluster. So which basically has the you have like a more and more higher and higher luminosity, and also like then the mass would be just like not changing a lot. So then if you have like a higher L over M, then you will actually see at the older population. So we basically compare these two things and then plot on the other alpha on the y-axis and then the L over M on the x-axis. We basically see the really nice correlation, one-to-one correlation. And then we also compare these the analysis to the other previous studies of the age estimation, and then it basically are quite consistent. So we can basically see, okay, see alpha versus L over M basically tells us about the other protocluster evolution. So we know that, okay, which is the oldest and which is the youngest.
Yeah, also in the grossest sense, we know what really is the oldest area because there's a revealed star cluster there, so it's old. We know the youngest area is the youngest area because that is where all the present massive star formation is occurring, and there's not really much happening anywhere else. So there's still a reservoir of material there for more and more star formation to be occurring. So that also jives with everything we learned from our evolutionary indicators.
Yes, the back and then the front.
This is a question of David. A fascinating talk. You said that the mass of the halo is now estimated to be 10 times more than it was before. Is that right?
Yeah.
That sounds like the amount of missing mass or dark matter that you need. Is that something you've been thinking about?
Yeah, we'll definitely be talking about that, or discussing that more and trying to refine that number. So there were some assumptions that were made in making that calculation, and we're working with some collaborators to basically work on more sophisticated simulations of how the hot corona gas and the cool leading arm gas basically interact. So there's some complexities that could move that number around a little bit.
Leslie Sage, Nature. This is for Adrian and David. It's kind of a technical question. So at 116 million years, the O and B stars are long gone. So you're looking at A stars or maybe blue supergiants. Do you know which type of star you were looking at?
Well, it's 116, so it is. There are still some B stars in the cluster. And so that's what we think are the tip of the blue main sequence that we were seeing. So mainly B and A stars are what we observed. Yeah.
Okay.
Hi, Camille again from Sky and Telescope. You actually hit it on a point, Adrian and David, earlier that I was wondering about. Are the properties of the stream gas such that we're sure they could form stars? Like, could you give us temperature? Could you give us density? And you mentioned this lineup with the knots, but wouldn't when the stars form, they have blown away the gas? So does that mean anything?
Yeah, those are all great questions. So we weren't ever sure whether stars could form in the leading arm or trailing stream gas. And it's also kind of metal poor gas. There's not a lot of metals in there. I think the fact that we do find these stars indicates that they were able to do it. So the densest knot actually is probably likely where most of them formed, and they were probably above the threshold when star formation could be happening.
The other, I think, important piece of the puzzle is the stars and the leading arm, they lead the Magellanic Clouds. So they've actually already passed through the outer part of the Milky Way disk. So though the outer parts of the Milky Way disk have fairly low density gas as well, there is the potential that they could interact somehow and form stars and continue on. That's all story time. I think a lot needs to be done to figure out exactly whether it's possible.
Let's check in with the chat briefly. Rick, do we have any questions?
Yes, we have one from freelance science writer Randall Hyman. This is for Alyssa Goodman. He asks, does the rad wave's sinusoidal form imply that it is oscillating? And if so, does that oscillation explain our passing through it 13 million years ago?
That's an excellent question. The answer to the second part is probably no. The answer to the first part explains the answer to the second part. So is it oscillating? So we've tried to look at the data from the few stars that have radial velocity and three-dimensional velocity measurements that are associated with the wave, the young stars, again using Gaia and also some other information. And we don't know yet what the pattern of velocity in 3 dimensions is. In the gas, we can only get the line of sight velocity, so it's a little hard to put that together. But what we do know is that Orion, which is a very large complex in molecular gas, that's at either the crest or the trough, depending on which way you look at the galaxy, so the peak of one of the waves, of the wave, is moving at 0 velocity with respect to the up and down motion with respect to the plane of the galaxy. So that if it was a wave that was oscillating, you would expect the part at the peak to be not moving because it's about to turn around. So that's good for a story that it would be oscillating, but we don't actually have detailed measurements of that. But in fact, it would be going up and down, and the sun's orbit and its orbit would cross kind of in the plane. And so that motion, going back to the second part of the question, is not really related unless I'm misunderstanding the question. That relative motion is more radial.
Well, let me ask the second half of his question then too and see if that clarifies. He
Sure.
says, since the wave is a stellar nursery, what might Earth's night sky have looked like 13 million years ago when we were in the middle of it? And do our respective motions imply that we'll pass through it again in 13 million years?
The answer to that one, the second part, is yes. Our respective motion does imply that we'll pass through it again in 13 million years. That's a very shaky conclusion at the moment. That's based on modeling of the orbit of the sun and the orbit of the wave and the other. And so, we sort of put that in the paper, and, Leslie led us, with our fingers crossed like this, but we're not sure about that one. And then what was the first part of the second question? Sorry.
Since the wave is a stellar nursery, what might Earth's
what
night
would the
sky
night
have
sky
looked
look
like?
Yeah, it would look great. It would look fabulous. All these beautiful nebulae, like the Swan nebulae that you saw, all the massive star formation that would be going on 13 million years ago would have been a lot closer and a lot easier to see, and possibly kind of all around us in a lot of directions if the sun was really in the wave, and assuming that those regions were forming stars 13 million years ago, which they probably were.
And then Larry Marshall, who's currently a freelance writer and used to be deputy press officer, is asking a follow-up question. Is there any relation between the Radcliffe wave and density wave theory? Is it perhaps a higher harmonic or a different mode of waves than the one that forms the spirals?
Oh, that's a very interesting question, and again, sort of in a perpendicular direction. So, density wave theory would cause the waves within the plane of the galaxy, and this is a wave perpendicular to the plane of the galaxy. So, the short answer would be no. But Gus, where'd Gus go? Gus, do you have a different answer to that question?
I think it's unclear how applicable density wave.
Well, we could give Gus a microphone.
I think it's maybe a little unclear how applicable density wave theory is even
to the Milky Way,
yeah.
right? Yeah,
Adrian, you might have also something to.
Right. Tell her that the density wave theory is very much at question in the Milky Way. You should talk to Lars Hernquist and other people like that.
Okay, that's it from the chat.
All right. One question here.
Jonathan Tan from University of Virginia and Chalmers University, Sweden. This is for Adrian and David. When we think of star clusters, we think of them often as gravitationally bound systems. Your cluster is particularly unique in being so widespread on the sky. So can you tell if it's gravitationally bound from the stellar motions? And if it is, does that require dark matter to bind it?
Yeah, from the rate of velocities, we found that the scatter dispersion of them was quite large and much larger than you'd expect if they are bound. And also, as Adrian said, they're spread out over a large region of the sky. And so we actually have been talking about whether we should actually be calling it a stellar association than a stellar cluster, and they likely formed in different parts along the leading arm.
This is a follow-up again for Adrian and David. You're probably going to say, no, there's no chance. But I wanted to ask, have you been able to image other stars to get data on other stars at the same distance with the same radial velocity profile elsewhere in the HR diagram other than these blue A and B stars to be sure that you aren't fooling yourself that these are like straggler stars or some other weird thing you might encounter?
Mm-hmm.
That's a great question. So it took Magellan even to get these high-resolution spectra for the brightest stars, and Magellan is a big telescope. So it's a good question whether we can go to a lower resolution instrument and go farther down the main sequence, but we haven't done that yet. So that's a great follow-up.
But we also got follow-up photometry from the dark energy camera, which was significantly deeper than Gaia gave us, and we saw the sequence continuing down farther than Adrian showed.
We're just about out of time, so if there's one final question. Oh, we do have one in the chat. Cool.
No, we have one from Rick Feinberg. So I guess since I only have one question, I'm going to ask James and Wanggi, because you were talking about how there's different stars within this nebula have formed at different times, and that's a discovery in the Swan Nebula. But is there anything particularly unusual or unexpected about that? Don't we also see, sequential star formation, for example, in some other nebulae like Orion?
Okay, that is also a really excellent question. So we are, so I'm not quite sure if I can say this or not, but I actually see evidence which is actually against the sequential star formation activity around there. So and I'm like, so if you actually expect that, like, if the oldest population in the middle of the Swan Nebula basically make the other, and like it's basically like the feedback basically make the other all this kind of like omega shape, then those all shapes should have their similar ages, but we basically see kind of like a different various evolutionary stages. So I will say, okay, this probably is basically showing the feedback mechanism which is acting as the other negative kind of like the triggering mechanism, like of the stellar cluster formation around there.
Yeah, and again, to your question, there's been speculation that there could be inside triggering that, as Wanggi was talking about, could trigger what we see as the V shape of the Swan Nebula. But that doesn't seem to be the case because, as Wanggi said, there's different ages. There's also another cluster to the north that is quite massive as well, and there was speculation there might be triggering downwards, and so that maybe the whole Swan Nebula has sequential star formation going down along it. But again, the ages don't work out. There's not a gradient of ages in that direction either. So we don't see evidence of any kind of triggering. That's not to say there isn't any triggering happening. Like you said, there could be triggering there. The influence could be quenching star formation as well. But that's all speculation. All we can do is just look at relative ages of the regions, which we did. Yeah.
All right, thank you to our speakers. Before we go, I'd like to remind everyone that the coffee and snacks in the press room are provided by University Space Research Association. So if you see USRA Public Information Officer Surya Faruqi around, please thank her. So big thank you to everyone for coming, and for those who tuned into the live stream, have a good day.